and next JK flip-flop and T flip-flop. Today we'll discuss how these codes we can execute in the EDA playground. So in EDA playground we can only simulate the waveform, but we can't see the hardware. So I wrote some codes related to these flip-flops. First, we'll see so EDA playground. This is the open source. So you can so this is EDA playground. So click on this edaplayground.com, and so here we need to write the design, and here you need to write the test bench. Okay. So if you see the first code for SR flip flop. Okay. So SR flip flop. So just this is the code. So here I am using a procedural statement, that is case statement. Okay. So you can use the procedural statements as for loop and case statement also. So last class I told you the for loop, sorry, you can use if else statement or you can use case statement. Okay, these are the procedural statements. Okay, so this is the code for SR flip flop module, and what is my module name? SR flip flop. So input clock. Okay, so input reset underscore n. Okay, this is the nomenclature yesterday I told you. If it is active asynchronous active low reset, I need to declare with reset underscore n. Okay, so active low reset means what? When it is 0, this will be activated, and when it is 1, this will be deactivated. Okay, that is given to the clear signal. Okay, and how many inputs are there? Two inputs are there, yes and r, and outputs you need to declare with reg data type. So output reg q. Okay, and output q bar I'm initializing with wide data type only. Okay, so I'm using if it is a wide data type, I'm using a continuous assignment statement, that is q bar equal to not of q. Okay, so before this I'm assigning these value, that is q bar equal to not of q, and always at the rate passage of clock or negate of reset begin. If not of reset, okay, q equal to 0, and else begin. Okay, so that is, this is asynchronous active low reset. Okay, passage of clock or negate of reset. Okay, if reset equal to 0, I am initializing the output to 0, q to 0, and else begin case, and I am using concatenation operator s comma r. So 2 tick binary 0 0, so that means q equal to q, that is memory state, and 2 tick binary 0 1, q equal to 1 tick binary 0, that is reset state. 2 tick binary 1 0, q equal to 1 tick binary 1, that is set state, and 2 tick binary 1 1, 1 tick binary, that is x, this is invalid state. Okay, end case end. So this begin you need to end, and next this begin you need to end, and this begin you need to end, and end module. Okay, here this begin also you need to end. Okay, so uh, so end module. Okay, this is the code, and so yesterday I told you the truth table for SR flip flop, D flip flop, JK flip flop, and T flip flop. Okay, so you need to remember the means sequence. From SR you will get D flip flop, from JK you will get T flip flop. Okay, so that you need to remember. And next, this is the test bench. So here if you see, uh, so module TB SR flip flop. So whatever the clock, reset underscore n, yes and r, these are the test bench variables. I need to declare with reg data type, and y q and q bar I need to initialize with right y data type, and you need to instantiate the design. Okay, so how you need to instantiate uh, design name followed by instance name. Okay, and whatever the variables outside the bracket are nothing but design inputs and outputs, and whatever the variables inside the bracket are nothing but test bench variables. Okay, and next you need to generate the clock, always hash by clock equal to not of clock. So here two more instructions you need to add when you are executing in EDA playground. So this is waveform setup for EP waveform. Okay, so that is dollar dump file, dump dot vcd, and dump wars one. Okay, these two instructions you need to add. Okay, for getting the waveform. Okay, so these two instructions are not there in the EDA Xilinx Vivado, but when you are using EDA playground, these two instructions are common. You need to include in the test bench. Okay, and initialize the reg variables. What are the reg variables? Clock equal to 0, reset underscore n equal to 0, and s equal to 0, and r equal to 0, and you release the reset. Okay, so hash 10. So we, for 10 time minutes, you need to release the reset. That is deset the reset. After that, for every 10 time minutes I am giving the driving the stimulus. Okay, s equal to 1, r equal to 0, this is set state. S equal to 0, r equal to 0, this is memory state. S equal to 0, r equal to 1, this is reset state. S equal to 0, r equal to 0, this is the memory state, hold state. And s equal to r equal to 1, that is invalid state. Okay, so after 10 time, after 20 time minutes, so dollar punish is a system task, you need to finish the simulation. Okay, next you need to stop, like you need to end the simulation. Okay, dollar stop is nothing but you need to pause the simulation. Okay, dollar finish is nothing but you need to end the simulation. And so you started with initial begin, no? So that is you need to end this. Okay, you need to end this. And again, very here, this is initial begin, so this begin you need to end. So this is for this end, initial begin. A dollar monitor you are using. Dollar monitor means what? If there any change in this variables, it will display. Okay, end and end model. Okay, this is the test bench. Okay, so this one I am executing in EDA playground. Okay, so how to execute in EDA playground? First, this code is there, no? So just copy this and go to EDA playground. And one second. Here you need to write the design. Okay, this right side you need to write the code. Okay, so write the code. And test bench left side, select all, copy. And next here paste. Okay, so next in the tools, and so language means you are using system verilog or verilog. Okay, you are using verilog only. That language is this system verilog or verilog. And so that is test bench plus design. Okay, you are using system verilog or verilog. And in tools and simulators, you can use Icarus Verilog. This is Icarus Verilog is there. Okay, these are the free simulators. Okay, Icarus Verilog. And you need to select this open EP waveform after run. Okay, you need to select this open EP waveform after run. And just you run this code. Waveform will be opened. Okay, so you'll get the waveform. If you observe here, so this is reset underscore n, no? So when reset equal to 0, q equal to 0 only. Okay, the output will be 0 only, and q bar equal to 1 now. And when reset becomes reset is deasserted, during the passage of clock I need to see. Okay, during the passage of clock, r equal to what? R equal to 0, s equal to 0. So this will be in the previous state. Okay, what is the previous state? Memory state. Okay, memory state. And during this passage of clock, r equal to 0 and s equal to 1. Okay, so r equal to 0, s equal to 1 means one second. Initially q is 1. Okay, initially, one second. Here during this passage of clock I need to check r equal to 0 and s equal to 0. Okay, r equal to 0, s equal to 0, q equal to 0 only. During this passage of clock, uh, s equal to 1 and r equal to 0. Okay, this is s and this is r. Okay, s equal to 1 and r equal to 0 means what? Set state. It is going to 1. Okay, set state. Q is going to 1. Just observe Q only, not Q bar. And during this passage of clock, okay, this passage of clock. So what is s? S equal to 0 and r equal to 0. This will be in the previous state only. So what is the previous state value? Previous state value is 1. So it will be in whole state only. Okay, memory state. And during this passage of clock, what happens? S equal to 1 and r equal to 0. So it is going from set state to reset state. This is nothing but reset state. Okay. So when s equal to 0, r equal to 1, this is reset state. During this passage of clock, okay, during this passage of clock, s equal to 0 and r equal to 0. This will be memory state only. Okay. And during this passage of clock, s equal to what is s equal to 1 and r equal to 1. So that is nothing but invalid case. Okay, q equal to you are getting invalid case. Okay, so like this you need to analyze in the EDA playground. Okay, So here also in the log file also you'll get the output. Okay. So see here, initially when reset equal to 0, s equal to 0 or equal to 0, it will be in previous state. That is initially q equal to 0 and s equal to 0 or equal to 0 memory state, whatever the previous state is there. S equal to 1 or equal to 0. Okay. Here this case s equal to 1 and r equal to 0 set state, and s equal to 0 or equal to 0 memory state, and s equal to here s equal to 0 or equal to 0 memory, this is reset state, and again memory state, and here you got invalid state. Okay. So like this you need to analyze the code, that is whatever the test code design and test bench, and the output in the log file and as well as waveform. Is it fine? Do you understood? Any doubts or queries in this? Shall I move forward? This is SR
Yes.
flip-flop. Okay. So next, what flip-flop I need to analyze? Tell me from this. So your choice. Can anyone tell me which flip-flop I need to analyze? I wrote for
T,
four flip. D flip-flop. Huh?
T, T
T.
flip
Huh?
flop.
Okay. T. Okay. Yeah. So remaining, I think remaining you can practice. Okay. So if you see the T flip-flop, this is the design code. So here you see. So module, what is this is test bench, and this is my design. Okay. Uh, so here you see module T underscore flip flop. Input, what are the inputs? Clock and reset underscore n. This is nothing but asynchronous active low reset, and input T, and output reg q. Okay, output, as this is a behavioral modeling, you need to initialize the output with reg data type, and output q bar. This is y data type only. First, you need to initialize with continuous assignment statement. Assign q bar equal to not of q. So whatever the q bar is there, you are getting the complement of q. Okay. Always at the rate passage of clock or negate of reset begin if not of reset. That means what? If reset equal to 0, you are clearing the output to 0. Okay, you reset the output to 0. And else begin, I am using if else statement. If t means what? If t equal to 0. So yesterday we already seen when t equal when t equal to 0, it will be in memory state. When t equal to 1, it will be in toggle state. Okay. So that we already seen the truth table. Last class I told you just to go through that PPTs. Okay. So based on the truth table only I'm writing. So if t, so that means what? If t, when t equal to 1, it will be in which state? It will be toggle state. So the q is non-blocking with not of q. Q is non-blocking with not of q. Else else means what? When t equal to 0, so this will be hold state, q equal to q. Okay, this will be hold state, and begin you need to end again. This begin, always after always this begin is there, no, this you need to end and end module. Okay, so this is the code for t flip flop. And coming to the test bench, so module, my test bench name is tb underscore t flip flop. So whatever this clock, reset underscore n and t, these are initialized with reg data type, and q and q bar I need to initialize with y data type, and I need to instantiate the design. Okay, this is connection by name. So whatever the variables outside the bracket are nothing but design inputs and outputs, and whatever the variables inside the bracket are nothing but test bench variables. And next you need to generate the clock, always hash by clock equal to not of clock, and initial begin. So for getting the waveforms, as I told you, know, required for waveforms for viewing the EDA playground, you need to use these commands. You need to remember dollar dump file. These are the system tasks. Okay, dollar dump file, dump dot vcd, dollar dump vars one. Okay, these commands you need to use. And next you need to initialize the reg variables. Okay, so whatever the steps I am told in the test bench, that only I am following. Step 1, you need to declare the reg variables. Step 2 is nothing but instantiation. Step 3 is nothing but generating the clock, and step 4 is nothing but initializing the reg variables, and step 5 is nothing but giving the stimulus, driving the stimulus. Okay, So step 5 is first, here you applied the reset, no? So reset equal to 0. For 10 time minutes you are releasing the reset, and for 10 time minutes I am giving t equal to 0. T equal to 0 means what? It should be in hold state or it should be in memory state. Okay, and t equal to 1 means it should be toggle state. Again, t equal to 1 means it should be toggle state, and t equal to 0 means it should be memory state, that is hold state. Okay, and after the 20 time minutes I need to finish the simulation. Okay, end. Okay, this begin is there, no? This begin I need to end. I need to monitor the signal output of the signals. For this, initial begin dollar monitor. Uh, so dollar monitor is nothing but a system task. If there any change in this variable, then it will display. Okay. So time also I am displaying. Time is the one data type. No, that means time also I am displaying. Time equal to percentage 0t. Reset equal to, this is the format specifier, percentage b, and p is percentage b, q is percentage b, q bar is also percentage b, comma dollar time. We need to declare the time with the dollar time. Reset underscore n, t, q, and q bar, end and end module. Okay, so this one I am executing. So go to design. Where is my design? This is design. So just select all, copy, go to EDA playground. So paste in design. Okay, this is paste in design, and this is the test bench. Select all, copy, and go to EDA playground and paste here. And so make sure that tools and simulators you need to select IKRS Verilog 12.0, and this should be tick open EP waveform after run. Okay, run this code. Now waveform is open, so I can analyze the waveform. See here, when reset equal to 0, q equal to 0 only. Okay, when reset equal to 0, q equal to 0 only. Okay, here till reset equal to 0, all the outputs will be in 0 state only. When reset is 1, you deasserted the reset. Okay, so when reset is 1, you deasserted the reset. During this passage of clock, t equal to 0. T equal to 0 means what? It will be in previous state only. So what is the previous state value? 0 only, no? So it will be 0 only. Okay, again here during this passage of clock, t equal to 0, so it will be 0 only, that is reset state only. Okay, and during this passage of clock I am making t equal to 1. Okay, t equal to 1 means initially q is 0, so t equal to 1 means what? Toggle state. So it becoming 0 to 1, 0 to 1. Okay, and during this passage of clock, uh, t is 1 only. Okay, so it will check. Okay, flip flop is nothing but edge trigger. The output will change during the set edge. Okay, so I given in the sensitivity list, that is passage of clock, no? So I need to check in the passage of clock, during this passage of clock. Okay, edge, when it is going from 0 to 1, that is nothing but edge. So if you see here, it will check for t. T is 1 means this will be in toggle state. So 1 to 0, it will go into 1 to 0. Okay, and during this passage of clock, if you see, during this passage of clock, again I am making t equal to 0. T equal to 0 means it will be memory state only. Okay, so what is the previous state? 0, so it will be 0 only. And during this passage of clock, during this passage of clock, t equal to 0 only. So when t equal to 0, it will be in memory state only. Okay, you can see the in the log files also. See here, dollar monitor I gave, no, in the test bench. So if there any change in the variables, any variables, it will display. Okay, so when reset equal to 0, all the outputs will be 0 only. Okay, so when reset equal to 1 means what? You are removing the reset. Okay, that means it is going from reset mode to functional mode. You are desetting the reset. Okay, so so t equal to 0, what? Q equal to 0 means t equal to 0, q equal to 0. Again t equal to 1, t equal to 1 for every 10 time minutes I need to check. Okay, t equal to 1 means q equal to toggle state, it is going to toggle state. Okay, Again, t equal to 0 means it will be in the previous state only. Okay. So t equal to 0 means q equal to 0 only. Okay. So like this. Here t equal to 1 means what? Toggle state. It is going from 1 to 0. After that, t equal to 0 means it will be in memory state. Okay. So like this, you can see the output in the EDA playground. Is it fine? Do you understood?
Yes.
So counters also we can see. So counters also yesterday we discussed about counters. So I will say one counter. So that is 1 second. We discussed synchronous up counter, no? So this is synchronous up counter. Uh, so here the code is same only. So code is same on like module synchronous up counter 3 bit input clock reset underscore n output range 2 down to 0 always at the rate passage of clock or negate of reset begin if not of reset count equal to what 3 tick binary you are resetting the output of all the flip flops. Okay, 3 flip flops are there, no? 0 0 0 else count equal to you are incrementing the counter. Okay, this is my code. And coming to test bench synchronous up counter. Okay, so just see here. So here whatever the so first you need to write the module and module name. Okay, test bench name and clock and reset underscore and you need to declare with range data type and this 2 down to 0 count is 2 down to 0. No, I'm using a vector 3 bit and next you need to initialize the means instantiate the design connection by name. Okay, with order list, sorry, with the name connection by name and you need to generate the clock. Okay, always hash by clock equal to not of clock and initial begin you need to use these two commands dump file dump dot vcd dump vars 0 comma tb underscore 3 bit counter. Okay, initialize the signals clock equal to 0 reset underscore I am applying the reset. Okay, after 12 time units I am releasing the reset. Okay, let it will count for 0 to 7 roll over twice. Okay, so that's why I am giving the time period delay. I need to run this counting for 150 time units. Okay, so if it is one time means I can give half of this. Okay, okay, half of this I can use dollar finish. Okay, and I need to see the means outputs display the outputs in the log file. For this I will use dollar monitor. Okay, if there any change in this variable then it will display. Okay, so go to the design synchronous counter, no? Synchronous counter select all copy and go to EDA playground in the design save this design and test bench select all copy and here you can see in the test bench. Okay, so here uh, run the code. You're getting error once again unable to clock reset and three bit up counter. This is 3 bit up counter only. Save this file and run this code. Once you could, you are getting error.
19 we need to make that same as TB name, right?
Okay, okay. Instantiate, no?
Yeah.
Synchronous up 3 bit. Same synchronous up 3 bit. 3 bit is there. Uh, Unable to bind wire. Uh,
Ni- 19th line where we dump bars,
90,
right? So should we take
uh,
as TB 3-bit up counter or
3 bit,
3-bit underscore up counter?
3 bit
Or
underscore up
up,
underscore counter. Okay, counter. Okay, save this file and run this file. Yeah, you got. Yeah, yeah. Is it fine? Yes, so you are getting this. Thank you for uh, giving the this. So see here. So when reset underscore in is zero, it will be zero only. Okay. So count is zero only. So when reset underscore becomes one, it will go into the functional mode. So it will count from where to where, 0 to 7. Okay. After that, again it will start from again 0 to 7. So like two cycles we will get. Is it fine? Do you understand?
yes,
Yeah. Okay. So this is EDA playground. I'll share this code so you can practice this. Okay. And mm, I'll open the EDA Vivado. So what is decade counter? What is decade counter? Decade counter is nothing but the
10
synchronous
bits.
10 bits. Yeah, it will count from 10 bits. I think you can practice that decade counter also. It is there in the code. Shall I explain the decade counter or not required? You can go through that, no? Decade counter. Hello. And 4-bit
Yes,
counter also.
sure.
Yeah, 4-bit counter also. Here you say 4-bit counter means just the only change is you need to you need to change the size only. Okay. So what is the size? Output range 3 down to 0 count. Okay. Count equal to count plus 1. Okay. This is my design and this is my test bench. Okay. So in the test bench, same process. So you need to declare count with wire and clock comma reset with ridge, and you need to instantiate, you need to generate the clock and making clock equal to 1, reset equal to 1. During the passage of clock, I'm generating this count. Okay, I'm running for 300 time units. Okay, this is 4-bit counter and counter using parameter is also there. Okay, counter using parameter. Okay, counter I'm opening. Counter using parameter. This is counter using parameter. Okay. So here parameter means what? Suppose uh, when you are designing any IP or SOC, okay. So after giving into the customer, we can't we can't change the parameters. Okay. Suppose you designed a 3-bit counter. Okay. But client or customer is asking that I don't want 3-bit counter. I want 4-bit counter. I want 8-bit counter. So in that situation, I can't change the design. Okay. If you are giving the fixed values, I can't change the design. So in that situation, dynamically I can change the size of that counter. So in that situation, I can use parameter. Okay. So how to write the code for the parameter? So module synchronous counter param. So ash parameter. I'm initializing size equal to what? 4. Okay. Here if you give size equal to 8 means it becomes a 8-bit counter. Okay. Size equal to 4 means it becomes a 4-bit counter. Okay. So input clock reset underscore n and input up input this is up counter. Okay, input up counter and output you need to declare with the reg data type 3 down to 0. This is 4-bit counter and I'm using asynchronous active low reset, that is always at the rate passage of clock or negate of reset begin if not of reset. Okay, if not of reset, so if reset equal to 0, so whatever the count value is there, I'm non-blocking with 4 tick h. H is nothing but hexadecimal. Okay, so it four size. So I'm initializing with the count value will be initialized. The output of all flip flops will be initialized to 4 zeros. It will be initialized to 4 zeros and else begin. If so, this is up down counter. It is acting as a up down counter. So I am using a control signal that is up. Okay. So else begin if up equal to 1, it should act as what? Up counter. Count equal to count plus 1 tick binary 1. Else else means what? When up equal to 0, it should act as down counter. Count is non-block unit, count minus 1 tick binary 1, and uh, so you need to end this. Okay, again this begin is there, no, this you need to end and end module. Okay, so this is the counter design by using parameter. And coming to the test bench, so this is the test bench parameter. Okay, uh, so here first you need to declare the variables test bench signals. Okay, clock reset underscore n and up with reg data type, and 3 down to 0 count with that data type, and next you need to instantiate connection by name, and next you need to generate the clock. Okay, first initialize the clock. You can use forever also. Forever hash by clock equal to not of clock, and next you need to drive the stimulus. Okay, drive the test vectors. Okay, initial begin. First I am making what? Reset underscore n equal to 0, and after that up equal to 1. Okay, and I'm making reset underscore n equal to 1. I'm removing the reset. Okay, and I'm running for up counter for how many time minutes? 170 time minutes. I am running for 16 clock cycles. Okay, I'm running for 16, as this is a 4-bit counter. So mod of a counter is 2 power 4. 2 power 4 means mod 16 counter. Okay, this is a mod 16 counter, and test down counter from 15 down to 0. So for this down counter I need to make up equal to 0. I need to run for 160 time minutes. Okay, and after that again I'm applying reset equal to 0, and next after that I'm making after 25 time minutes I'm making reset equal to 1, and repeat it means what? I told you in the procedural statements, no, so it will be repeated for 3 times. Okay, so up equal to 1 for 50 time minutes, up equal to 0 for 50 time minutes. Okay, so 3 up counts and 3 down counts I need to see. And simulation after 20 units 20 time minutes I need to end the simulation, and next dollar monitor, if there any change in the variable then it will display. Okay, so this I am going to execute in Vivado. So open the Vivado. Last class we already seen the synchronous counter, no, same project I am opening. Okay, go to the sources. Okay, add the design sources, create the file. What is my file name? One second. What is my file name? Synchronous param, no? Yeah, param. This I am closing. Uh, yeah, synchronous param. So this is my design name. Just copy this and give the file name as same. Choose the location. Choose the location. So RTL counters. Select. Okay. Finish. And the module name is also same. Yes. Now synchronous param. My design is created. Just remove this. Remove this. And go to synchronous param. This is test bench. This is my design. Select all. Copy and paste here. Save this file. Save this file, and go to simulation, add simulation, create. Okay, what is my test bench file? Test bench file is this one, synchronous counter param tb. Copy, and here choose the file where you want to save this file. Okay, finish. My module name is also same. Finish. So my tb is created, this one is created. Okay, so my tb file is created. So just remove this, and whatever the code is there, select all, copy, and paste here. Save this file. Now under synchronous param, I got the DUT file, that is my design file. I got DUT synchronous counter param. Okay, and if you want to see in the top module in the design source, okay, if you want to see the netlist, right click on that synchronous that design file and set as top, and next this one also you need to set as top, and you need to see the elaborated design, run the elaborated design. It's reading the netlist. So you got the waveform. This is nothing but up down counter using parameter. Okay. So that is counter edge 3 down to 0. So 3 down to 0 means you have like 4 D flip flops and one more 2 cross 1 mux, and you have adder as well as subtractor. Adder for up counter and subtractor is for down counter. Okay. So like this, one more, two more, three more signals like clock, up, and reset underscore n. Okay. So how this our tool is converted your code into gate level netlist. Okay. So just close this and run simulation, run behavioral simulation. Have you given in the text bench dollar monitor he given? So dollar monitor you given, no, it will be it is displayed in the console. Okay. So first you given count equal to 0 means what it is will do up count. Okay, from where to where, 1 to f. Okay, 1 to f. After that it will come to the initial state. Okay, and next what you are doing, you are making the up equal to what, 1. Okay, so up equal to 0. Okay, up equal to 0 means what, it will count down, it will act as down count. Okay, so down count means 0 f e d up to so on, it will count up to 0, up to 0 here. Okay, again you are giving randomly, no, so that is repeatedly it is doing up count and down count, no. So that means here from, so you are giving up equal to 1 means it will do up count, and next up equal to 0 means it will do down count, and again up equal to, so repeat 3 means it will be repeated for 3 times. Okay, so this output you can see in the waveforms also. See here, just a fit to page, so you will get this one. Okay, so you just zoom this. uh, so if you see here, just to zoom this. Yeah, so here so it will do first when reset equal to 0, so it will be in reset state only. Okay, so when reset becomes 1 means it will do counting, it starts counting. So 0 1 it will be initial state and it will count from 0 to f, till here it will count. Okay, 0 to f. After that, so in this position up equal to what, 1. Okay, so normal it will do up count, and after that here again it will come to the 0 state, and here it becomes 1, and now I am making uh, up equal to 0. So up equal to 0 means initial state, it will start from the initial state 0, and it will start from f. Okay, f e d e b. Okay, like that it will come to the initial state, like initial state. Okay, and next I'm making up equal to 1. So till 5 it will do till uh, till 5 it will do up counter, and 5 4 again, till 4 it will do up counter again, down counter, up counter, down counter, like this 3 times. Okay, I'm checking the up counter and down counter like this. I'm checking for this waveform. Okay, so do you understood the concept of parameter, and this is nothing but up down counter? Any doubts or queries? Shall I move forward?
Yes.
Yeah. What about others? Yeah. So next, I will start. So I will share this course just to practice this. So already I shared. So in the EDA playground also we can see that EDA playground the folder I will share. Okay. So next we will start with this shift registers. Okay. So next we will start with shift registers. What are these shift registers? We'll see. So shift registers. So shift registers, I think in digital you already seen. One is SISO, next SIPO, and next is PISO and PIPO. Serial in, serial out, serial in, parallel out, parallel in, serial out, and parallel in, parallel out. Okay. So here first we will see the SISO code. Serial in, serial out, serial in, serial out, 4 bit. So 4 bit means you are using like 4D flip flops. Okay. So in digital you already seen this concept. Just I am revising. So here 4D flip flops will be there. So leftmost bit is MSB of the flip flop. Let us take this is D3, Q3, and D2, Q2, and D1, Q1, and D0, Q0. Okay. So this is connected. So D3, Q3 is connected to D2, and Q2 is connected to D1, and Q1 is connected to D0. As this is a synchronous sequential circuit, common clock passage of clock is given to all the flip flops. Common clock is given to all the flip flops. Okay. So common clock is given, and here from here you are giving the data like 111. So this is my SISO. Okay. So SISO, and uh, so so here first what you need to do means first you need to write the code for D flip flop on the top mod D flip flop, and next you need to instantiate 4 times. Okay, that is nothing but structural modeling. Okay, structural modeling means what? First you need to write the code for D flip flop. Okay, and after that you need to instantiate how many times? 4 times. Okay, so if it is a behavioral modeling, how to write means if it is a behavioral modeling. So behavioral modeling. So here SISO, serial in, serial out. Okay. Suppose initially the output of flip flops will be what? 0 only. Okay. Output of flip flops will be 0 only. So that is 0, 0, 0, and 0. Okay. So these are the indexes 3, 2, 1, 0. Okay. So every time when you are doing the, suppose if you take from here, this is left shift. Let us take this is left shift. See, so okay, from here you are taking. Okay, so 1 1 1 1. It may be right shift or left shift. Okay, so if it is left shift, so you are giving the serial in data, whatever the serial in data from here. Okay, so first what happens? So 1 1 1 1 means this one will be loaded. So this one will come here, and this will be shifted. So that means it will get 0 0 0 like this will get. Okay, so that means first one will be loaded in this state, and this will be shifted. So again, so here so initially this 0 will be shifted, and this 0 will be shifted, and this 0 will be shifted, and this will go. Okay. So what happens here? Uh, so left shift now, yeah, left shift. Mm, so now this is for one clock cycle, first clock cycle. Second clock cycle, what happens? This one will come here, whatever the vacant position. This you are loading with one, and this 0 will come here, and this 0 will come here. Okay, and next, so this is second clock cycle. A third clock cycle, again one will be loaded and this will be shifted. Okay, this will be shifted and you are getting uh, so 0 over here. Okay, this is third clock pulse, and at fourth clock pulse what happens, all data will be loaded. Okay, all data will be loaded, and uh, so so this will be shifted, this one will come here and one will come here, this one will come here, whatever the vacant position is there, that will be loaded with the uh, 1. Okay, so that means here every time this 3 to 1 values are there, no, this will be copied, no, every time. So now, so here this 00 value you got here, again after that these two values you got here. Okay, again these three values you got here. Okay, and if you consider one temp register. Okay, so this serial out data, whatever the serial out data is there, that is coming into the temp register. Okay, so I can write, so how to write, suppose if you take one CISO, so this is one CISO system, serial in serial out. You have, what are the inputs? You have clock and one more reset. Okay, and serial in, serial underscore in. This is one bit. Okay, and next you have serial out, serial underscore out. Okay, this is also one bit. You are getting the data at serial out. Okay, so that means at fifth clock pulse, this one will come to the temp register. Sixth clock pulse, this one will come to the temp register. At seventh clock pulse, this one will come to the temp register. Okay, so at seventh clock pulse, all the data will be come to the temp register. Okay, so how to write, that is temp equal to, I am using concatenation operator, temp temp. So this I am initializing with temp register. Okay, this I am loading with in the temp register. Okay, so temp, that is 2 down to 0, and from left what you are doing, you are serially you are inserting the data, serially serially you are inserting the data. Okay, so how to write the code? So have you understood the logic, how I am generating the logic in this? So left shift operation, shall I move forward or shall I tell once again? Anyone give response so that I will move forward.
Yeah, you can move forward.
Yeah, yeah. Anyone having any doubt in this? Yeah. So for how to write the code? Module, module, SISO, SISO underscore 4 bit. This is my uh, my code, and input clock reset, and what are the input data, serial underscore in. Okay, and output serial underscore out. Okay, serial underscore out. Okay, first I need to declare a temp register. Temp register, what is my temp register? 3 down to 0, one temp register. This is 4 bit, no, so first one I am initializing the temp register. Always, always at the rate passage of clock, always at the rate passage of clock, begin, begin if reset. Okay, begin if reset. Okay, if reset equal to 1, I am initializing temp with non-blocking 4 tick binary 0000. H also, H means 1 bit I need to give. Else what I need to do, temp is non-blocking with temp of 2 down to 0 comma serial, serial underscore in. Okay, serial underscore in, this is nothing but left shift. You are doing which operation? Left shift. Okay, left shift, and end. Okay, end, and at last so this is wide data type, this is nothing but wide data type. So at last after end I need to use the continuous assignment statement, assign serial out, serial underscore out, that is blocking with temp, where you are getting the output. So you are where you are getting this output temp 3, no? Where you are getting the data serial out at the temp 3 only you are getting. Okay. So that I am initializing. Okay. So serial underscore out equal to what I am initializing to temp 3 with blocking. Okay. End module. End module. Okay. So this is left shift. Okay. If it is right shift, so what will be the change? So if it is right shift, suppose if it is right shift, what you are doing? So 3, 2, 1, 0. Okay. This is MSB bit. Okay. This is LSB bit. Okay. First initially all the registers are 0 only. Okay. First clock pulse you are right. You are inserting one bit. This is from the left. You are inserting serial underscore in 0, 0, 0. Okay. And after that next clock pulse this will be shifted. Okay, this 1 will come here, 0 will come here, and 0 will come here. Again you are inserting the data. Okay, so this is first clock pulse, second clock pulse, third clock pulse. Again this will be shifted. This 1 will come here, this 1 will come here, then this 0 will come here, and 0. And fourth clock pulse, here you are inserting 1. Okay, you are inserting which data means 1, 1, 1, 1. Okay, so this 1 will come here. At fourth clock pulse, this will be shifted. 1, 1, this will be shifted, and this will be shifted. Okay, 1. Okay, and at fifth clock pulse, what happens? Here, whatever the backend position is there, that will be loaded with 0, and this will, 1 will come here, and this 1 will come here, this 1 will come here. Okay, and so you are getting this I am initializing with temp register. So you are getting the serial out data at a temp 0. At a temp 0. Okay. At 60 clock pulse, this 0 and this will be shifted 0, 1 and 1. Okay. At 7th clock pulse, 0 will come here and this will be shifted 0. Again, this is 0. Again, this is 1 you will get. Okay. So how I can write so how many clock pulses are required to get the output? 7 clock pulses are required to getting the output from the SISO. Okay. So I can write the logic. If it is right shift, temp equal to, just this logic will change. Okay, in the code. That is, uh, so you are inserting the data. Okay. So from the left you are inserting the data. Serial underscore in and comma. Every time which one is copied? This one is copied, no? So this one is copied. Okay, this one is copied here. Again, next clock pulse, this one is copied here. Okay, this one is copied. So I can give temp, that is 3 down to 1. Temp 3 down to 1. Okay. At last, I need to use this assign serial out, serial underscore out. That is equal to what? I am getting the serial data at temp 0. Temp 0. Okay. So this is the only change I need to use. Is it fine? Do you understood? Shall I move forward? Any doubts or queries? Just please respond so that I will move forward. Okay, fine.
Yeah.
Okay. Coming to the test bench, same thing. So CISO for the test bench module. So we need to first declare the module. So module. What is my so CISO underscore 4-bit underscore TB. Okay, and next you need to declare the internal variables. Declare the internal variables. What are the internal variables for the test bench? So for this clock, reset, and serial underscore in, that you need to declare with the reg data type, and wire and serial out. Whatever the serial out is there, I need to declare with uh, wide data type. And step 2, so this is step 1. You need to declare the internal variables. Step 2. Step 2 is you need to instantiate the design in the test bench. Design in the test bench. Okay. So what is my design name? SISO underscore 4 bit, and instance name is DUT, and I'm using connection by position with order list. Okay, how you declared the input and output, that same order you need to follow. Okay, serial underscore in comma serial underscore out. Okay, in the design, how you declared the inputs and output, that same order you need to follow. Okay, that is the connection by position with order list. And three step 3, you need to initialize the reg variables. Initialize the reg variables. Okay, so initial begin, what by using concatenation operator, clock reset, and serial underscore in, I'm initializing to 0. Okay, end. Okay, and step 5, you need to generate the clock. Step 4, generate the clock. Okay, so generate the clock. So I'm using always #5 clock equal to not of clock. And step 5, driving the stimulus. Okay, driving the stimulus. Okay, you can give the delays also, or you can give at the neck edge of clock also. Anything you need, you can follow. Initial begin, this also you try at the rate neck edge of clock. So first I am applying the reset. This is in the so this is active high reset, no, synchronous active high reset. That's why reset I am applying reset. After that I am removing the reset. Okay, neck edge of clock, reset equal to 0. Okay, and at the rate neck edge of clock, I am giving serial underscore in, that is equal to 1. And after that, at the rate neck edge of clock, okay, serial underscore in, that is equal to 1 I am giving. And at the rate neck edge of clock, serial underscore in, that is equal to, I am giving the 1. 4 values I am giving at the rate neck edge of clock. I am giving serial underscore in equal to 1. And end module. This is my SISO program. Okay, is it fine? Do you understood the test bench? For the sequential circuits, test bench is same only. 5 steps are there. Okay, the test bench is same only. These steps you need to remember. Okay, so we'll see the SISO. Shift right, shift left, shift right. Okay, this is shift left, shift right. This is universal. Okay, this is universal shift register. This is universal. Like this also you can write the code. My code also you can follow. Okay, one second. Here synchronous before universal shift register. Universal. Yeah, this is universal shift register. Okay. SISO you can try. One second, it's there or not. So this is universal shift register. It will shift left, shift right, and after completing all the shift registers, I will tell you. Yeah. So this is about the shift register, and this is SISO. Okay. So one more code I will tell you, that is SIPO. SIPO means what? Today we'll discuss these two, and next class we'll see PISO and PIPO. Okay, PISO and PIPO. So next is you try this code and try to execute in Vivado. So next is SIPO. SIPO. SIPO means what? Serial in parallel out. Okay, serial in parallel out. Okay. So how many clock pulses are required to get the data? So SIPO means you already seen. Okay. So four clock pulses for loading the data. Pulses are required for loading the data. Okay. For serial data in. Okay, serial data in, and one clock pulse is required for taking out the data. Okay, during parallel out, you require only one clock pulse only. Okay, parallel data out, parallel data out. Okay, so here if you see this diagram, so you have SIPO, serial in parallel out. Okay, so what are the inputs? You have just a clock and next reset. Okay, and next serial underscore in, serial underscore in, and one more signal, that is load. Okay, so one more signal, that is load. Okay, when load equal to 1, it will do the load operation. Okay, loading the data. Okay, like that. And next parallel out, parallel underscore, one second, parallel underscore out. Okay, this is SIPO. If you write the code, Verilog code, for this RTL code, if you write, okay, first module SIPO, my module name is SIPO, input, clock, reset, serial underscore in. Okay, serial underscore in, output. Output is how many bits of data? 4 bits of data. So that is, if it is a 4-bit shift register, so 4 bits of data means you need to declare with a vector 3 down to 0, parallel out, parallel underscore out. Okay, parallel underscore out, and I need to declare a one temp register, reg 3 down to 0, temp, 3 down to 0, temp, and always at the rate passage of clock, always at the rate passage of clock. Okay, um, so begin. Okay, if reset, if reset equal to 1, temp, whatever the temp register is there, that will be loaded with all zeros. Okay, 4 zeros. Else, okay, you are using left shift. Okay, so when you are using left shift, so that means left shift means, as I told you, no. So first 0 0 0 0 will be loaded with temp register. Okay, so first from here, from right, the data will be loaded. Okay, so this is the same concept, 3210. After this is one clock cycle. Second clock cycle, what happens? One will be loaded and this will be shifted. This one will come here, this 0 will come here, and this 0 will come here. At third clock pulse, what happens? This one will be loaded and this one will be shifted. One will come here and 0 will come here. At fourth clock pulse, what happens? One will be loaded. You are loading 1111 data in the SIPO. Okay. So one will be loaded, one will come here and one will come here, and here one will come here. So at fifth clock pulse, what happens? This total 4 bits of data will be parallel out. 4 bits of data is coming to the temp register. Okay. So total clock cycles are required. So as I told you the concept, every time this will be copied. Okay. So this will be copied. So every time. This will be shifted and this will be copied here. Okay, 0 1 1, again 1 1 1, here you are getting. Okay, so for the left shift, what I am doing, that is temp, I am using concatenation operator. Okay, so that is temp, so temp, that is what, 2 down to 0, 2 down to 0 comma, from the right you are you are means you are adding the, serial in data. Okay, so that is serial underscore in. Okay, comma serial underscore in, and so from the right you are inserting the data. Okay, and next assign parallel out, parallel underscore out, parallel underscore out is 4 bit, no? So where the data is coming, to the temp register. Okay, to the temp register. Temp register is also 4 bit. Okay, so that is the non-blocking with temp register. Temp register and end module. End module. Okay, so this is about the SIPO. Do you understood the SIPO? Any doubts or queries? Waiting for your response.
Yeah, but do you use assign inside always?
One second, one second. Uh, okay, one second. Here, parallel out where I declared, here I declared, no? Okay, so one second. Sorry. Here, here I need to use that means here I need to keep end. After end, I need to use assign. That is parallel out equal to temp. Parallel out equal to temp. This is parallel out equal to temp. I can't use assign in the behavioral, the always block. After always block, I can use assign parallel out equal to temp. Now is it fine?
Yes.
Okay. Yeah. So just to practice this codes and come with any doubts or queries. So next class we'll see with the code execution and as well as the codes for previous like PISO and PIPO. Is it fine?
Yes. Yes.
Okay. Yeah. So come with the whatever the task I gave. Okay.